In this lecture, we'll talk about how sensors can mount active attacks against clients who are attempting to communicate on the internet. We'll start by talking about denial of service attacks, and then we'll proceed to investigate more sophisticated examples of denial of service attacks, including reflection attacks and the so-called Great Canon. In the first part of this lecture, we'll explore denial of service attacks. The denial of service attack is an attack on availability, and it can take many forms. It could involve destroying hardware, for example, cutting a network fiber, attacking software, modifying software in a subtle way, or corrupting packets in transit. It could also involve an attack that overwhelms a client with a prohibitively large amount of traffic so that it's unable to respond or communicate in any productive way. Blatant denial of service attacks can have a bunch of ramifications, including bringing down entire internet services by crashing the server or overwhelming the server by using up available resources. A denial of service attack can also exhaust network resources, in addition or as an alternative to exhausting client resources. A denial of service attack is simply an attempt to exhaust resources. There are a number of finite resources in a network service that an attacker could attempt to exhaust. For example, network capacity or bandwidth, the resources that an operating system allocates for connections like TCP connections, or server resources in the case of an application like a web service, a website, a streaming video service, and so forth. Denial of service attacks are typically high-rate attacks, but there are also so-called low-rate denial of service attacks, which are even more difficult to detect. There's also a variant of a denial of service attack called a distributed denial of service attack, where the attack comes from many distributed attackers instead of just a single attacker. Early denial of service tools were single source, meaning there was a single place on the network or internet that launched the attack, and they were launched against a single target or destination. In many cases, the attacker doesn't need a response from the victim, and so it's possible for the attacker to even spoof or lie about the source IP address, in other words, the origin of the attack, making it sometimes difficult to trace back the attack to its origin. We'll also see some examples of something called amplification, where an attacker can send a small amount of traffic that results in a large amount of attack traffic being produced, often from a number of distributed points on the internet. Denial of service attacks are sometimes preceded by reconnaissance or so-called scanning attempts, and they can be launched manually by hand from a single source host or automated from a large network or army of compromised hosts, sometimes called a botnet. Let's first explore attacks on transport or TCP. Recall that TCP has a connection setup phase called a three-way handshake. The first part of that handshake involves the client sending a so-called SYN packet to the server. Now, by default, at that point, the server needs to remember that the client is going to return with an acknowledgement in the third part of the handshake, and so that initial SYN might result in setting up some connection state at the server. Now, hopefully you can already see the problem here. The client didn't have to do any work before the server had to begin storing data on the client's behalf. Specifically, each arriving SYN requires the storage of state at the server in a so-called TCP control block. It's small, but recall that the client didn't have to do any work to cause that state to be created. And so by sending a lot of SYN requests, an attacker can cause a server potentially to store a lot of state for a bunch of half-open connections, thereby exhausting resources and resulting in the rejection of legitimate requests. Such an attack is called a TCP SYN flood, where we exploit the fact that state is allocated at the server after the receipt of an initial SYN packet. So an attacker can simply send a SYN packet and fail to reply with the subsequent acknowledgement. A server typically has a finite queue size for incomplete connections, and so once that queue is full, it can't accept any more requests, including legitimate ones. The underlying problem here is that the client isn't authenticated before it's sending these packets and before the server allocates resources. And so an attacker can send many connection requests, spoofing the source IP address because it doesn't care whether it receives a response. And if the source address itself is valid, there's really no harm done. Any source that receives such a SYN-ACK packet would simply send a reset back to the victim, but the attack can proceed as intended. This is what that might look like graphically as a client sends a repeated number of SYNs to a server while failing to respond with any acknowledgments. Early examples of classic SYN floods date back to the early 2000s. One such SYN flood attack was launched by a so-called internet worm, or a piece of software that spread itself around the internet, infecting vulnerable hosts, compromising them, and then using those compromised hosts as the source of attack. All of those compromised hosts then sent a so-called SYN flood to a victim, in this case, windowsupdate.com. The design of the internet makes it very difficult for the victim to block this incoming traffic, particularly if it's coming in a distributed fashion from a wide array of sources. In this particular case, the Microsoft solution was to simply relocate the server to a new domain name. But of course, that solution isn't necessarily always viable, particularly for popular websites. An idea that's now in widespread deployment in defense of so-called TCP SYN flood attacks are so-called TCP SYN cookies. The general idea here is when the client sends a SYN with a particular sequence number, the server responds with the so-called cookie, which is a sequence number that is selected as a function of the client's source address, port, the server's destination address and port, and some random secret that the client doesn't know. Now that sequence number is generated with a cryptographic hash, so even with knowledge of that sequence number, the client would have a very hard time reproducing this for an arbitrary source address and port. An honest client can, of course, respond with the second part of the three-way handshake with an acknowledgement to the sequence number. And at that point, the server can check the response. If the acknowledgement matches the expected sequence number, the connection is established. But note that after the second step, the server did not need to establish any state so that it could remember the client in the third part of the three-way handshake. In summary, denial of service attacks exhaust some limited resource, such as network bandwidth or server resources. These attacks are typically high volume, but they're not always high volume if the attacker can manage to launch some low-rate attack that's asymmetric in its exhaustion of the victim's resources. Early denial of service attacks involved TCP, including so-called SYN flood attacks. In subsequent parts of this lecture, we'll now look at some more sophisticated denial of service attacks.